We've already calculated unit tangent vectors, derivatives of unit tangent vectors, and unit normal vectors. Let's make sure we understand what these vectors are telling us. If we have a vector function r of t tracing out a path according to parameter t, if t is interpreted as a time parameter, then our velocity as a function of t will be the derivative of r, and in any case the r prime vector is going to be tangent to the curve, whether t is a time parameter or not. The direction of that r prime vector, interpreted as a velocity vector, can be indicated by a unit vector. Excuse me. To get this unit vector, all we have to do is divide the velocity vector by its magnitude, and that should be a familiar operation, and we call that the unit tangent vector. Easily obtained if we want to do this in general terms without the velocity interpretation, that is without interpreting t as a time, then in general that's just r prime over the magnitude of r. Now, if we have motion along the curve, we could have a velocity clock time t, a velocity clock time t plus delta t, and this particle could be speeding up or slowing down. That is, your v of t and your v of t plus delta t might well have different magnitudes, and that might continue as delta t approaches the limit. So first thing we see is our delta v, which is just this vector, is not generally perpendicular to our velocity vector. And that's only going to be true if, as in preceding clips, the magnitude of the velocity vector remains constant in the limit. So here's our picture in terms of our unit tangent vector. Okay, now our unit tangent vectors that would correspond to these two velocity vectors would both have the same magnitude because they're both unit vectors, so that the delta t forms this side of an isosceles triangle. So delta t has magnitude 1, so this is an isosceles triangle, and as we've seen recently, that implies that delta t is in the limit as t approaches 0, delta t will become perpendicular to our unit tangent vector, and that the derivative of our unit tangent vector with respect to t must be perpendicular to t. So this gives us a strategy for finding a unit vector perpendicular to the unit tangent vector. Now, we did something similar when the magnitude of r remained 1 using the u theta and u sub r vectors, and could have been done using a variety of other techniques. We showed that the r prime vector was perpendicular to our radial vector and could then have acceleration, second derivative components perpendicular to and parallel to the unit tangent vector. Now, in this case, the r vector might be in this direction. As a matter of fact, if we look at this picture, the tangent vector to this curve is not perpendicular to our r vector. So in general, that's not going to be the case. That was a special case that applied when the magnitude of r was constant. In that case, we found that it was convenient to have a component of the acceleration in the direction of motion and a component in the direction perpendicular to motion, and we want to do something similar here, but we have to do a little bit more work. Okay, so here we have a unit tangent vector. Now that vector is a function of time, and as we see here, it can change from one time to the next, giving us a change in the unit tangent vector and eventually allowing us to understand the derivative of the unit tangent vector, which we've seen to be perpendicular to the unit tangent vector. It follows then since the derivative of the unit tangent vector is perpendicular to the tangent vector, that unit tangent vector is normal to the curve. And our unit tangent vector and our derivative of the unit tangent vector are therefore going to be perpendicular. So we define what we call the unit normal vector n to be the unit vector in the direction of the derivative of the unit tangent vector. Okay, unit tangent vector is perpendicular to the unit tangent vector. If we divide it by its own magnitude, we get a unit vector that's perpendicular to the unit tangent vector. In addition, this vector is going to point in the direction perpendicular to the curve, in the direction of the acceleration vector, if you will. If the curve is curving like this, then the unit normal vector is in like this. The unit normal vector is perpendicular or normal to the curve and directed toward the inside of the curve, if you will. Of course, that's a little bit circular because we use this to we use the unit normal vector to specify the orientation of the curve. In any case, we call this the principal unit normal vector, and we're going to see how it can be applied